We're going to talk about titrations, and titrations are based on neutralization. So this is when you combine an acidic solution and a basic solution so that the H plus and the OH minus concentration are equal. So basically acid plus base yields what we call a salt and water. Now a salt can be any ionic compound. Remember that ionic compounds are electrolytes because they ionize when you put them into water. So you guys are familiar with neutralization mostly because you might see like antacids, Tums. You know, if you have heartburn or something like that, you take the Tums and it will neutralize the acid in your stomach. So the learning target, we're going to use this M1V1 equals M2V2 formula to solve the titrations, and we're going to interpret titration graphs, okay? And of course the honors, we got the honors target here using stoichiometry. All right, now titration is the laboratory method that determines the concentration of a solution. So we have a concentration that we know, and we use stoichiometry. A couple of terms. Equivalence point is where you have neutralization, H plus equals OH minus. The end point is where you see a color change with an indicator. And we'll look at a couple of these. So the end point and the equivalence point should be really, really close. All right, so we have our example here. Now this is on your practice paper that you got. So with 89.2 milliliters of 0.765 molar sodium hydroxide is going to neutralize 50 milliliters of HCl. What is the concentration of acid? Now the formula looks like this. NaOH plus HCl, we get salt and water. So we are going to use M1V1 equals M2V2. So make sure that your 89.2 milliliters and your 0.76 molar goes together. Oops, sorry. And make sure that 50 goes with our unknown concentration. And so when you solve this, you get a concentration of 1.36 molar. Now you have these titration curves on your sheet. So what we need to do is label where our endpoint should be. So when you have a strong acid titrated with a strong base, you're going to get a curve like this that has this really sharp dip here. So the endpoint is going to be right here in the middle where the pH is 7. Okay? Now if you have a strong acid and a weak base, your endpoint is going to be a little bit lower than 7 because the pH of the acid of course is lower, and you're going to have more ionization going on here. Weak acid, strong base, endpoint is a little bit above 7. And then when you have a weak acid and a weak base, there's a lot of what we call buffer action. So you have a more slopey line. Like there's no big, straight, steep drop off. But the equivalence point is going to be pretty close to 7 for that. So make sure you label all of these arrows and know that those are the end points. All right, a couple of things I just want to talk about. Indicators. These are chemical dyes that change color at a specific pH, and we're going to see a few of these in class. Now, you can look at them. They look like a little rainbow, and they change colors in different pH ranges, so that's a really neat little graph there. And they're also used in what we call buffers. Now buffers are going to resist changes in the pH, and they're especially useful in your blood. You've got a lot of buffers in your body because you don't want the pH of your blood changing too much. It's slightly basic, so you don't want it to get too acidic, and you don't want it to get even more basic. So I'm also going to show you how to do stoichiometry when you're not at a 1-to-1 mole ratio, when you're not using M1V1 equals M2V2. And this might be a high proficiency question for you. So I've got the same example here that we used before, and I just want to go through these steps with you real quick. So if 89.2 milliliters of 0.765 molar NaOH neutralizes 50 milliliters of HCl, what is the concentration of the acid. So we are looking for molarity of HCl. We know that we have 89.2 milliliters of 0.765 molar NaOH, and we know that we have 50 milliliters of HCl. So we start our box the same way with our X's. Now our conversion factor here, though, to find moles, we're going to have to use our molarity formula. So here's our molarity formula. Molarity equals moles divided by liters. So I just rearranged that to solve for moles. So moles is molarity times volume. So to get moles for sodium hydroxide, we have to use this formula. So our molarity is 0.765 molar. Our volume is, and we have to change this into liters, 0.0892 liters. So if we do the math on that, sorry I didn't do this ahead of time, we end up with 0.0682 moles. Now this is moles, so this is what's going to equal X. So X is 0.0682 moles. So of course our X over here is also equal to 0.0682 moles. And then we plug that into our formula. Alright, so now we have moles, 0.0682 divided by liters. Now we have 50 milliliters, so we're going to change that to 0.050 liters. And when we do that math, we end up with a molarity of 1.4 molar HCl, which is what we got when we did M1V1 equals M2V2. Now let's look at what happens if we don't have this 1-to-1 ratio here. So in this problem we have 40.8 milliliters of 0.106 molar H2SO4 sulfuric acid. It's required to neutralize 50 milliliters of KOH. What's the concentration of the base? Alright, so KOH is our base. We're looking for molarity if we have 50 milliliters, okay, and we have 40.8 milliliters of 0.106 molar H2SO4. So to get X here to solve for moles, we do have to use our molarity formula. Alright, so moles are going to be equal to 0.106 times 0.0408. We just changed our milliliters to liters. So that's going to give us moles equal to 0.00432. Alright, now this is going to be equal to X because it's 1X. So we're going to do 2X to get moles of KOH. So 2 times that is going to give us 0.00864, and that's moles. So we're going to plug that into our formula down here. 0.00864 divided by, we have 50 milliliters, so 0.050 liters. So make sure you change that. And your answer is, oh, where my pen go? 0.173 molar KOH. So you do have to take into account your mole row and the coefficients in front of it if you don't have a 1-to-1 mole ratio.